Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video, another video in our series of videos dealing with set theory, is going to concentrate on what's known as the Principle of Inclusion Exclusion. This is basically a counting principle, okay, and it's really good, and it's probably one of the more I suppose, especially from an introductory level, is one of the more important concepts that will really come in handy when you're dealing with set theory and when you're trying to solve different types of problems. And I'm going to present two applications of it. Well, I'm going to first present actually the principle of inclusion exclusion for the 2 set case, and then also for the 3 set case. But let's just concentrate on the 2 set case first of all. So what I'm going to do first is I'm just going to draw a Venn diagram. Okay, so a Venn diagram is it's just a diagram. It's a diagrammatic representation of sets. The important thing about our sets is that our sets are made up of objects. Okay, objects fall into particular sets because they have some particular property associated with them. Okay, but the main thing is that all the objects that exist are always relative to some universe. So we have a universe, okay, and in this case, let me just draw the universe, a bounded universe, okay. So the universe is bounded by this particular box. I'm just going to say U here, like that, to represent that this is the universe. And I'm going to do a 2 set representation. So we have 2 sets, okay. Here's the first set, okay. And it's possible that, we'll call this set A, and it's possible that this shares some commonality with another set through an intersection, which we'll call B, but it's not always the case. But if it's empty, it's empty, okay? In which case they're mutually exclusive. But for this particular application, let's just assume that there is an intersection. Okay. So what we'd like to be able to do is we'd like to be able to come up with a formula, okay? An equation, let's say, okay, that allows us to count the universe, count how many objects there is in the universe, but have the total count of the number of objects in the universe relative to how many things are in the set A, in the set B, and how many things are outside of the set A unioned with B. Okay, so we're interested in the size of the universe. So let's put that down mathematically. So what we'd like to be able to account for is the size of the universe, and these 2 vertical lines, we've defined these in an earlier video, represents the cardinality of the universe. In other words, how many objects are there in the universe? Okay. Now let's just try to rationalize initially about the size of the universe. Well, the size of the universe has to, I suppose, contain, or the size of the universe has to contain part of its count. It has to be how many things are in the set A. So let's just put that down here for a moment, yeah? So the size of the universe has to include how many things are in the set A, okay? And it also will have to include how many things are in the set B, if that makes sense, okay? In the set B, okay, and we'll also have to include how many things are outside of this particular boundary, the boundary around A, B, which is, well, this particular set here, okay, around this particular boundary is A unioned with B. So we're interested in everything outside of A union to B. So the size of the universe has to include also how many things are outside A unioned with B. So actually A unioned with B is, let's say, complement, and I'll just put a little C here to represent complement. So at this particular stage, what we're saying is the size of the universe must be at least equal to the size of the set A, how many things are in A, plus how many things are in B, okay, and also how many things are outside of A unioned with B, okay. So let's just see where we've counted, and let's just put a little tick in the rooms that we've counted. So I've counted everything in A, in room A. So that means I've counted all the people in this part of the room, and I've also counted all the people in this part of the room, okay? Because they would be characterized to be in A, albeit they're in the part A intersection B, they're still in A, okay? So these 2 ticks represent what's in the set A. Okay, what's in the set B? Okay, well, it's everything in this part of the room, along with everything in this part of the room. So we've counted everything in B, and we've symbolized it by a tick. And we've also counted everything outside of A union B, okay, which is A union B is complement. So what we've done is we've counted here, okay. Now, hopefully what you can actually see is that we've counted all the possible rooms, but in one circumstance we've actually double counted. Okay, we've actually overcounted the size of the universe because we've double counted this portion in the middle here of A and B, which is known as A intersection with B. So how am I going to compensate for that? Well, say if I take away one of the amount of things that are in A intersection with B. So what I'm going to do is I'm going to take away minus how many things are in A intersection B. Okay, so let's do that. So if I take it away, I'm going to put a cross here to indicate I haven't counted it. Okay, because I'm taking away one of them. Okay, one of the totality of what's inside A intersection B, or I'm taking away the cardinality of A intersection B. And this particular expression here is what's known as the principle of inclusion exclusion. Yeah, you can see when we count the size of the universe, we're including with the pluses. Yeah, these are all positive values. We're including, okay, these particular cardinalities, and we're excluding this cardinality here. Okay. This is really good because actually allows us. It's an equation. Yeah, we have the inequality sign there. It's an equation that allows us to balance. If we're given information about the size of the universe, if we're given information about A, we're given information about B. We're also given information about A intersection B. Well, we can always find out how many people are outside of A union with B. In other words, how many people aren't in them particular sets. Maybe we'll be given the size of the universe. We'll be given how many things are in B, how many are outside it, and we're also given how many are in the intersection of A and B. Well, then we can also, because this is the only thing that's unknown, we can find out how many things are in totality, how many things are in A. Okay, so this is, I suppose, the principle of inclusion exclusion, and it's the principle of inclusion exclusion for the two set case. Now, let's have a look at the three set scenario. Okay, so let's do a Venn diagram for the three set scenario. Okay, so once again we'll bound our universe inside a box. Okay, so let's do the box like this. Maybe we'll do a little bit bigger.